I'm sorry, it's not professor. Is it recording? Yes. Okay, so welcome, everybody. I'm going to present today about a method that I've been using the last time, which is topic modeling with large language models embeddings, which is a topic that has been very interesting in the whole process. It's going to be more like a methodological presentation. So I will do two parts. First, I will give an overview of BERTopic, which is the specific algorithm or framework that I used. Then I will explain how I used it. I will show a bit of the results, but mostly I will focus on like the process, on how I used it, because I think it's what is interesting for me to talk about, honestly. And finally, if we have time, I have some pieces of some sources that would be interesting to look and to reflect on the magic behind, which is mostly about the embeddings and what are they really capturing in large language models or in other AI models that are around, particularly generative AI models. So first, I didn't put my timer. I use BERTopic. BERTopic is a topic modeling framework based on BERT, which is some large language model. It was developed by some psychologists that turned into a data scientist. It's open source, so there is quite some documentation. There is a lot of people contributing, and I would say like a very interesting active discussion on the GitHub, and all of the people that are like constantly developing this. It's very active, I would say. I would say it's easy to use. If you have some familiarity with coding, I don't think you need to be a computer scientist to get into it. Once you get your data ready, which I think is the most struggling part, then it's just these 2 lines of code to feed the model, and then whatever visualization you want to put, which is, again, like 1 extra line of code to produce the plot that I will show later. This is some form of unsupervised learning for text data. It's some kind of AI inside in one step that I will cover more deeply later. But more importantly, it's a highly flexible and modular framework. Like it allows for a lot of tuning in the different steps. Like all of these are like bricks over bricks, and they can be changed for different methods, or the methods themselves can be tuned by different parameters. So first, we start with the embeddings, our first step, which is like where the current magic is happening, where we take text sequences and we convert them into numerical vectors, like some high-dimensional representation, numerical representation of these texts or documents. These sequences are huge. Like what I was using had like 300 dimensions. Large models have like from 8,000 to 12,000 dimensions. So yeah, there are a lot of numbers there, and there is a lot of research on understanding what these numbers are really capturing or embedding, what kind of information or things they are learning. But the basic assumption is that vectors that are close to each other, or embeddings that are close to each other, are similar, like either in their structure or in their semantics. Exactly how they're similar or why they're similar, that is ongoing research. This is just like what they started observing. They didn't train these models to output embeddings that are similar to each other. So for example, here we have 3 embeddings. That is a very happy person, that is a happy person, that is a happy dog, and today is a sunny day. So here clearly the today is a sunny day kind of diverge from these other sentences that we could argue why they're similar. Is it because they're all happy? Maybe. Is it because it's about someone or some person or dog instead of like the day, or talking about today as a temporal thing? I have no idea. Like you can try to guess. I think I have lost a lot of my own time trying to guess why. More importantly, there are like a variety of models that are fine-tuned for different tasks. Like you can produce embeddings that are looking for different things. So for example, in this sentence, we can either classify, and we could focus, for example, in these three sentences, okay, happy person, happy dog. They're kind of the same. We could say like, okay, these are sentences describing that someone is happy, whatever. Opposite to this one. So we will classify all of these together. So for that, we need embeddings that put them together. So we can group them, like we can visualize them as closer. We can calculate some closeness between them. Or we could be interested in the semantic similarity between these three. And in that sense, this sentence doesn't matter. And we want to like increase the distance between these vectors. So for example, we could say like, I don't know, I want to focus on the subject. Like, are they talking about persons or are they talking about dogs? Or intensity, are they talking about happy or a very happy? Like we can fine tune models to try to distinguish between these things. It's very dependent on the task. And well, there are models, of course, that are all-rounded, which is what I use. I didn't fine-tune anything. And there are many off-the-shelf solutions for different kind of tasks. It's important to note that large language models are not embedding models, even though they use embeddings internally. They're not designed to produce them. They are designed to produce the next token, to predict text, to generate text. Whereas an embedding is particularly trained to produce the embedding, to produce the numerical vector and stop there. And then to use that vector for classification, similarity, summarization, and different kind of tasks. But yeah, like in general, we can say that GPT is not an embedding model, but OpenAI has an embedding model based on GPT. But there are different things. Once we have our documents or text into, you see that I see that thing is up there. Is there a way to remove it? Yeah. Click move on. Maybe from the right. Is it this one? Mm-hmm. Okay. So once we have our, oh no. Okay. So now that we have our high dimensional embeddings, we need to reduce their dimensionality. This is a very common problem in machine learning and computer science when we have some task that involves hundreds of variables sometimes. The space between the different points on your data set, they became like kind of meaningless in high dimensionality. All points are kind of isolated, so it's different to find groups that are together. But there is almost always some inherent structure that captures differences between points. So for that, we use dimensionality reduction techniques to find the latent space that captures like its structure. So for this, unfortunately, we're always going to lose some data. So for example, we can look for this, like, I don't know, like spatial arrangement of colors based on its different features. Right now, I forgot what were the features. But so for example, from this step to the two-dimensional step, it makes a projection from the upper. It's like I'm looking for the cube from the upside. So I'm losing all of the information that is contained on this depth, this third dimension that I effectively removed. And the way they made it from the first to the two dimensions to the first dimension, I don't have any idea. But it's mostly to like show like there is some information that is lost. And there are several algorithms that are trying to find ways around, like to find the most effective, in a way, dimensionality reduction method, trying to capture these high dimensional structures. But in any case, it's a very complex challenge. In this case, they use UMAP, which is a uniform manifold approximation projection or something like that, where it's very good at capturing non-linear topologies, so things that are twisting. A manifold, for example, the Mercator projection, I think the globe map is a manifold projection of the Earth, like the surface of the Earth. And UMAP is particularly fast. So maybe some of you know the TS, how do you say? Yes. TSNE, which is another nonlinear dimensionality reduction method, but it's computationally very expensive. And in this case, when we are usually exploring topics or trying to explore different parameters, we need to be able to iterate fast, and we cannot waste like 2 hours for a method or something. Another alternative are like the principal component analysis, but it's a linear method, and it can enhance some interpretability of results, but in general, it struggles to capture like very complex structures or topologies into these high dimensional spaces. Once we have reduced this 300 or 8,000 dimensional embedding into some more manageable dimensionality, which is usually like 5 to 10 dimensions, we can start grouping documents together based on their embeddings. We can try to find like groups of them. So for this, we use clustering methods. In particular, I use, the framework use density-based clustering, a hierarchical density-based clustering, which basically just takes a random point, and start checking how many points are nearby. If there is enough points nearby, it includes all of that in that cluster. If there are no more points nearby, it stops and the cluster is defined. It starts randomly somewhere else. And there are 2 main parameters that are regarding like the cluster size and how it defines like these core points. I will also talk about this one later because, I like this part in particular. This algorithm allows for clustering without specifying the number of clusters, which is very important. There are other clustering methods that you need to define, like, okay, like we're looking for 4, 5, 10, 20 clusters, and you need to input that. Even though there are some ways around to like kind of like automatically explore and like find the most optimal solution. They usually like at least like the people who are like doing this topic model, they prefer to go with a density based, because we don't know the ground truth. We don't know the number of clusters that are there. So this method is really nice to try to find them. It's cluster shape independent, so it allows for different shapes, like not only circles, but like whatever shape can be defined as a collection of densely clustered like dots in hyperdimensional space.
Questions?
Yes, please.
So if you were looking at a particular space of text wherein you knew what it should be talking about, what topics should be there, or you have a hypothesis, could you then use plug in a different clustering method like k-means, so you get your k clusters that you think should be there, and then each cluster you can see, does it correspond to what your hypothesis was?
Yeah, but then the sense is like, okay, what I struggle to think in that approach is that, okay, like we have 2 different type of text, or we know like the groups, and we can attempt to do that. Like further down in the model, I explain a little bit on that, like some semi-supervised clustering of the topics of the groups. But then it's like, okay, if you have 2 different pieces of text that you distinguish either semantically or in the structure, how do you trust that the embeddings are going to capture that difference? Like maybe it can work, and I think like we never lose by trying it out.
Mm-hmm.
But I think like it starts with the assumptions that the embeddings are going to capture that. But I think I think it's a nice idea, and later when I show my results, I think there is a clear example on where that could have output a nice results. But I'm going to come back to that. Do you want to add something else, or?
No, I just thought, is it then the answer that you shouldn't do it here, but you should just do it later in the pipeline, what I was suggesting, or am I jumping ahead?
I didn't understand.
Never mind. We'll come back to it if it seems relevant.
Okay. Okay, so when we cluster in these first initial steps, we got the embeddings, the dimensionality reduction. We clustered those embeddings, and here we already defined our topics. Like we already have groups of documents together. We just don't know what they represent. So either we can start visualizing and try to make sense of the topics. But I would strongly advise against it, because if you are doing this topic modeling, it's because you don't have time or you have a large high volume of data. So the remaining steps, basically, I forgot my name. Yeah, they're not easy because you often interact with these big blobs of high-dimensional points projected into a two-dimensional graph. So then the three remaining steps, they take care of producing interpretable topic representation, which is basically giving labels to each cluster. So the first two work together to create a bag of words with the objective of extract the frequent words and filter out the stop words. This is a thing that you mentioned, or maybe someone else when we're doing this. The stop words are removed after the embeddings are produced, not before. And I think that is an important thing to say because the stop words like all of these articles, like they provide information, contextual information that the embeddings are learning to capture. So if we are removing them, then I think we're just unnecessarily removing information. So I think there are like some clever techniques applied here that they are using it to remove it, yeah, on this topic interpretation where they are already clustered and it doesn't affect the embedding of the documents. Once we have like frequent words for each cluster, there is this optional step that is called some fine-tuned representations where they use representation models, they call it. One example is keyword, which was made by the BERTopic developer, which basically takes the words, like the more frequent words, and it compares their embeddings to the average embedding of the topic. So if a word embedding is similar to the average embeddings of a cluster, then it's more like representative in their logic. You can also use GPT. So the way you can use GPT is, for example, you have a lot of documents in a cluster, you grab a subsample, you put the bag of words, like, I don't know, like this cluster is defined by, I don't know, sports, football, ball, player, score, whatever. You put 5 examples of documents in that cluster, and you ask GPT, give me a label for this. So GPT builds or interprets that topic. Or I think the funnier one is that you can be the representation model. Just look a subsample, check the most representative word, and come up with something. Like I think, honestly, I think that is one of the most important steps. Like don't get yourself out, especially at this part, because here is when you are trying to distinguish, okay, are the topics making sense or are they full of bad things? And lastly, even though it's not included. Well, this diagram is made by the developer. Okay, I don't claim any credit for this or any image that I put. I failed to put the respective sources because of a lack of time. I'm very sorry. I will try to mention, do the proper credits. And I would say like a very powerful thing of BERTopic is the visualizations functions that they offer. I think it was very kind of easy to use. Again, like I think the complex stuff is not like using it, but like adapting it or tuning it for any particular task. So to start, there is this document embedding visualization. I can maybe show, I think I have an example. But I cannot. How do I do this? So for example, this is our systematic literature review for the ones that have been reviewing. If you have been not, please go there. And these are like the 16,000 abstracts that you merged from one of the searches, the advanced search, which was the lower volume data that we have. But 16,000 abstracts is still like a very, very, very good number, like for this kind of task. And here we have like basically like, yeah, 16,000 dots that I could like start reviewing and trying to make sense. These are abstracts, so there is a problem in this visualization where I cannot see the full abstract. Thankfully, I didn't have that problem because I used sentences instead of the full abstract. But yeah, this is an example of what, some kind of output. Since the clustering is hierarchical, you can also find like here we have how many? 250 topics, which is an insane number in my head. But 53. Well, I didn't count the, did I? Oh yeah. Oh my God, I failed. And then we can see, I don't know the proper terminology to say a more wider collection of clusters or a granular. This is less granular. It's more granular. I have less topics here.
Okay.
So I am taking smaller topics and grouping them together.
Okay, so
it's the opposite, right?
but it shows 500.
Yeah, no. Okay, yeah. So the
okay.
the numbers here are just that they are made up afterwards. So they take two clusters from the beginning, they make a third cluster, they assign it another number and another bag of words. And these are the representations we're talking about. So without all of the last steps here, there will be a lot of like but, however, like blah 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 blah. But
it's about attention even.
Huh?
One of them is even about attention.
Yeah, that's pretty cool, right? Like
which focus attention. Which one?
Aquí, focus attention.
Attention.
Yeah, and that is the only one, I think.
So we can skip that.
Yeah, so maybe we should just focus on this one and remove all of the others. But yeah.
What about gray areas? What are they?
What? Okay, yeah. Thanks for bringing that up. The clustering will not assign every document to a group. There is always going to be outliers. So all of these gray dots are unclustered documents. They were not assigned any topic. There are some techniques to reduce the outliers. I will mention that later because I apply them also.
So another question.
Yeah.
Are they outliers for any level of granularity? Or...
No.
So when we start with lower levels, we have less outliers. So when we have more more clusters, we have less. Or the same. I don't know. It's
you cannot see here.
It seems that they're not changing.
I can talk about that. I will talk about that in a while.
Okay.
Because I face the same issue. Nice. Okay, so this if you don't have an overwhelming amount of documents, maybe I would use this visualization a lot to like assess whether your clusters are making sense or not. At least I use it for that. Next, we have the Jesus Christ. We have the intertopic distance map, which here each blob is a different topic, and this is trying to plot like the semantic difference or like the whatever difference there is between the topics capturing the embeddings. Like the further away they are, the more dissimilar they are supposed to be. Again, it could be semantic, it could be the meaning of the document, or it could be the structure, like trying not to make any strong, like there's not strong like knowing what is it, like until you review them. Until you review them, like I think you can actually make sense of many of them. So for example, I will not give examples. Then, because I will give them. And then you have like a similarity matrix, which tries to do a similar thing that the previous one, but instead of plotting it in 2D, is checking like the similarity between topics embedding. So for example, here we have a topic. Don't make sense of the labels because there were so many topics here that the labels are just some of them. Mm-hmm. So this one, for example, doesn't have a label. It doesn't have to do with the late in advance. That is the one over it. So this one doesn't correlate with most of the other ones. So I think that this is useful sometimes to like pick up some topics that are a bit like strange or have some anomaly. For example, in my data, it was about the references, like inline references, which didn't correlate with any of the other topics. So this kind of stuff. Then we have topic modeling over time. So if we have like some time variable associated with our documents, we can see when they were more trendy or not. So this is an example from Twitter. I'm not exactly, I think this was about Trump Twitter or like the Trump sphere Twitter. So there was this kind of like electoral cycle correlation where, I don't know, China and fake news and what was the other one? This yellow one, the border, security, and Democrats were like peaking. So I can guess we can understand why right? So I don't know, like this is, I think this one, even though I didn't apply, it could be very useful, for example, for what we're gonna do in Hypercog, if we ever go into like Twitch streaming or any kind of streaming of video game sequences, like when people are reacting more passionately, like if you have peaks of certain topics that you identify, then you can like make some sense of some kind of label or some kind of phenomena that is happening over that period of time.
Yeah.
And here they use years, but it could be anything, any other measure of time that you can.
Exactly what I had in mind, but I thought we would have to engineer it ourselves. So I'm very good.
Yeah, I will bring this also at the end, like some future thoughts. And then we have like topics per class. So if our data has class, for example, this is an example from the 20 news group, which is a toy data set. Like it's a big data set with already classified documents. So machine learners or use it to train custom models to test performance, etc., etc. So here we have documents that are already having a class. So for example, we have the scientific and cryptography group. And this group is mostly composed of key encryptions, key NSA, whatever. I think maybe it's only cryptography. I don't know what is the C related to. I don't remember. Then we have the sports and hockey, recreation sports and hockey, which is mostly composed of hockey and some other stuff. But yeah, it also has like the small presence of all other topics. And like other topics also, I got confused there. In any case, it's pretty obvious here that for each group, its label is going to be like very unique, like only dominated by one, because it's like it's being grouped on the groups that it should be. It's like self-recurrent in a way, like it's just a demonstration. Oh my God, I got so confused trying to explain.
I think the first word is the big group, then it's smaller group, smaller. So baseball is a group of sport. Sport is a group of recreation. So it's just baseball. Yeah. So cryptography is just cryptography. So
science, cryptography, society, yeah. Religion, Christian.
Yes.
Computer science,
so,
operating system, Windows, miscellaneous.
So only the last.
Is there some kind of news groups or something?
Yeah. There are 20 groups of news.
Yeah.
So there are news about sports, about cryptography, about electronics, but they're all different groups. So for example, the baseball group is different to the hockey, the sport. Sure. You know, they're two different sports.
Yeah.
So I will come back to this later because I have another graph about this, which is not any better. But the idea here is that if you have class, for example, I don't know, you have documents that come from one person or from one institution or for years, you can study how the topics that you identify are distributed in those classes. So in the first year or in the first group, what topics were more trendy? In the second group, what topics were more trendy? So it's some kind of distribution per class, which is what I actually use for my own study. Like this is what I use the most for my own analysis. So I will try to come back to that later. You wanted to say something?
Yeah, there just was the last topic. It's cool. TBI, FBI, fire,
gas, chill. Yeah, I think that is the politics and guns one.
Oh, okay.
Yeah. This also shows like indirectly like which ones are more frequent. You know, like this one is still about machine and hardware, but it's very small. I don't know if that is the proper thing. Or maybe they're not shown here because here they're like the top 10 topics probably.
That's because it's about computer systems, Mac and hardware, and Mac users never pay any attention to their hardware.
Yeah.
Oh, okay.
So there are less news about it.
Graphic designers, so they don't know.
Yes, excellent.
Yeah, so like the relative dominance of some groups in terms of frequency or volume in the documents. And then for each group, we can calculate, of course, like which are the most representative words, like the score of them. This is based on the bag of words. Like there is this TF-IDF algorithm. It's not exactly the same algorithm which they use. They tune it a little bit, but that extracts, like which ones are more frequent relative to the overall set of documents. So for example, in the sports topic, we have game, team, games, hockey players. Then we have like the cryptography, key encryption, phone, encrypted security. and so on and so on. Again, all of these graphs just help you to make more sense of whatever topics. And lastly, we have this token level topic distribution, which I also find pretty cool. So we have a sentence, the market for high performance video card that supports Visa local bus with blah, blah, blah. It decomposes sentence in tokens. It's in smaller pieces. It can be words. It cannot be words. In some cases, the token could be sentences in a document instead of words in a sentence. So this tokenization can also be on different levels. And so it tells, okay, which token contributes more to the classification of that document. In this case, we have a big contribution of these words into this group, the cards, driver, diamond, video, some kind of hardware group, but also in the motherboard, RAM, board, and in the PDA, I don't know what is the slot, PDS, LC news, I'm chewing around maybe, or I need more information about that topic to make sense of it. But clearly this is the higher contribution. And then we have other words that are contributing to other topics. So yeah, this is for more fine-tuned analysis on yeah, like a topic to cluster correlation. This is using embeddings also, like this is calculated using embeddings. It says?
I was wondering why some both have values.
Because they are not, I guess because they are not like associated with any others. I really don't know what is going on here, you know, because yeah, like every column should have values if they are using the embeddings distance, because you can calculate for everything.
Probably
But yeah,
they're smaller than 0.1 because you don't see numbers.
yeah,
Yeah, there's probably also a distribution calculation going on, like the market. Those words might be very lowly, like weak association with many of the topics, and therefore they don't stand out for any particular. So there's no information. But you can take the informativeness of it as a rule of thumb, like heuristic of what they're actually doing with entropy information. So.
Yeah, and also education, the second row, it doesn't have anything to, and you that was.
So there's no point
Yeah.
highlighting a cell if it's not, or
yeah.
the other way around, like how is it got a relationship? It's got to have a relationship through some kind of a statistical anomaly.
Yeah, there are some thresholds clearly applied here. And well, those are like most of the visualizations that come off the shelf, like on this BERTopic framework. They're all documented, they're like easy to implement, there is a lot of guides. But more importantly, any step here can be modified, changed, tuned. In particular, I would point out that different clustering techniques are important to check out, because that is the point where like I feel like the magic materializes and we got defined groups, even though we don't know what they are yet. That is the moment where we define them. So the parameters that define the clustering technique are very important. And the whole topic modeling here is very sensitive to whatever parameters you put there. And also the strategy itself. Like either you'll use DBSCAN or k-means or any other thing. And then the other one, of course, is the different embedding models. Like this is an ongoing, like very fast-moving, at least during the last years, field. BERTopic in particular, they recommend a lot to use this SBERT, which is sentence BERT, which are all like the BERT-based embedding models. But you can have GPT. Here you have Hugging Face, which is another source of like state-of-the-art embedding models. Right now, for example, I think the top performing one is one made by NVIDIA that they released like 2 weeks ago. And I was like, why I didn't see this before? And it was like, yeah, they released it like 2 weeks ago. And yeah, and they're like very diverse. Like some of them are weighing like 8 gigabytes. Well, the one I use is like 70 megabytes, like very lightweight, very fast, and very good as well.
Never until now understood what the hugging face was about.
It's a hugging
The name of
face.
the emoji, of course. I was wondering. is it
I've
something to
seen
do
I've
with,
seen peer-reviewed papers where they just put a hugging face.
Yeah.
Hugging face transformer. I
was
love
like,
it.
is it something to do with aliens? One thing I would say is that my intuition would be that dimensionality reduction is also very important.
Yeah.
If you get that with factor analysis, it really
Yeah.
it's a strong relationship with what you think is going on in the dependencies.
Yeah. Yeah.
Like are the
Yeah. No. I think it's a very important point. And if we have time to reflect, there is something I really want to point out about dimensionality reduction. The reason why I didn't include it here is mostly like what is both like very important, affects a lot, and is kind of easy to handle. I feel like the dimensionality reduction, we enter in a very ultra hyperdimensional abstract space.
very subtle.
So like, again, like any notions that we have in 3 dimensions, like we try to extrapolate to this high dimension, apply those logics, but is that really what's going on? Like there is very abstract mathematics, and I find it fascinating in reality. And that's why I have some funny examples at the end. But in terms of the practical thing, I think embeddings is just checking online, changing a string in a piece of code, and then you have a different embedding model. I want to know that in this, I don't know if it's SBERT and Hugging Transformer are web pages, and they have like different models they offer. And SBERT has a scientific embedding model. So it's particularly tuned to find a semantic similarity or differences in articles, like abstracts. So that would be really cool to use in the systematic literature review. For example, it's more specific to that. Well, so far I only been using a general model, not fine-tuned for anything in particular. So that brings me to my example. Do you want to take a break? We can make a 5-minute break.
Okay.
You can hate someone, you can throw things at me, you can watch memes. Okay, UC is there, nice.
Want to open the window? Sure.
Yeah. I think I do have it on virtual file. Maybe it's for you.
Don't worry, UC. It's good to have you here.
University of America.
Okay, can we continue?
5 minutes?
What was it?
5 minutes?
I will separate the group in the back.
2 more minutes
2 more minutes.
left in 5 minutes. Go in 5 minutes.
I've been sorry.
It should be somewhere.
Like in the hot places, you need
Yes,
the key.
yeah.
We should start bringing those.
Who is us?
Yeah, and those.
You see there now?
So
Yes.
it's, 6:30. I will double check with them.
Lauri told that he could not enter the Zoom. That's weird. I think there's an excuse.
He who is without sin passed through the eye of the needle. Or something like that. I don't know. Forget me. Church.
That's not good. Okay. Time.
Yeah, I'm trying my best.
Good, man. Always reliable.
Okay, next I will provide an example of what I did, how I use it. But is there any questions so far that you would like to make?
So there were question slash comment, but the prior section, it's just an illustration of the visuals, the ways that you can sort of get information out of the process. Because I feel like some people in the room who might wish to use it might feel like they're a bit lost so far.
Yeah, a bit of a.
But that should be fine, right? Because that was only supposed to show us the information visualization.
So the question, can you use it like for as a plug and play? So can you just use it? So you just have data, can you use it? So without any sophistication.
Yeah. It's 2 lines of code. Like if you have the data, it's just 2 lines of code, and then you have the visualizations.
Yeah, and
like
then
extract the
So
topics.
how do you need the data to be? Some rows in a CSV, each row being 1 line of text? 1 segment of text, a sentence or a paragraph or a whole
so
document in one.
it's a string. It's a string of text with a string. Yeah, it's just a string of text, actually. But each element could be either the full document, it could be a word, it could be sentence. You see what is the level of.
Yeah.
But yeah, it's just strings of text. You
You
can
can attach to each string of text something like a timestamp, participant ID,
like the model.
tabular, standard tabular data type of thing.
I don't know if there is a proper way to format your data because that is going to depend on your own analysis. So for example, if you want to fit time.
Sure, but just in your experience, you've got an example of having time on in the analysis. So where does it come from?
I didn't have time in my analysis.
No, you have an example that you showed us of
That's
having
something
time.
changed.
Yeah, it's just every string is associated with its own time. So for example, I don't know, like well, I can show a little bit of.
So in practice, the CS or the data would be just some tabular data with different columns. And the columns could be, one is going to be a string. That's your text. And the others could be a timestamp or the ID of
a class,
person or
a group.
A document that came from.
Yeah, of course. I mean, like, I think the more pieces of information you can attach to a string of text is always better.
Sure, in principle.
Like, but yeah, like the idea would be like to decompose your strings, like your text, and each row in that data set would be either a full document, a full sentence, a full word, depending on the level of topic modeling you want. In my case, it was a sentence level, like I analyzed sentences. So each row in my data set was a different sentence associated with a different person, associated with a different document type, and several other things. But what was important for the topic modeling itself it was I just could access the string, the list of strings. And then the other columns, I use it further down in my analysis. Like, so what we did was basically to extend my master thesis experiment, where I observed participants in interactions with ChatGPT. And this was an exclusively quantitative study. We just gather behavioral observations, we quantify that, and we look for associations, correlations. So our aim with this topic modeling was to include the qualitative data that we gather into our analysis without investing the huge effort that a full qualitative study involves, that it was not so feasible for our context. And in particular, we wanted to quantify the topical diversity in our participants' prompts with GPT and also in their written products, like in the assignments they produce later in the course. So why did we want to do that? Because it aligns with the framework that we use on our study, where we were analyzing like exploration versus exploitation behavior, which is about like exploring a broad diversity of topics, semantic diversity of topics, or exploiting and narrowing down into more specific content. So the kind of data that we have were reported interest, like the classic introductory assignment of any course, like, hey, I am Pip, I like dogs. No, I like cats more. Prompts of interactions with ChatGPT, which is what we collected as part of our study. The final course assignments, which were two, the study assigns and the essays. So I had all of these pieces of information. We had 25 study assigns, 22 essays, and 78 prompts. Maybe that was the higher number. So the issue that I have is that, well, we need to pre-process this text and I decompose it in sentences. Why did I do that? First, because these numbers don't represent a good sample size for topic modeling. Even though you can try to extract some things, it's gonna be very fuzzy and unreliable. So splitting it effectively increases the data points that are being clustered in the topic modeling technique. And also embedding the whole document doesn't capture the nuances of every particular document. So for example, one study design, if I embed the whole thing, I cannot rely that it's going to capture like the very particular details that might distinguish from others. But yeah, by separating in sentences, we are stripping those sentences from a lot of context. So it's a trade-off. Like in my head, the ideal way would be to input paragraphs, because I feel like paragraphs are what people usually make as a unit of content in a middle step between the sentence and the whole document. But there are not like easy, clear-cut algorithms or libraries available to split something in paragraphs. You could use GPT. I argue that you can make GPT read something and return you the paragraphs in CSV format or JSON format. It's something I didn't try because we ran out of API credits because someone stopped paying for it. But yeah, maybe that could be a potential solution because unfortunately there is no there are no libraries to separate in paragraphs. Not so in sentences. Like in sentences, it was again there is a tokenizer that splits whatever text into sentences as long as it's trained. In this case, it's a tokenizer in English. Ben?
Should I pay for more API credits?
Not anymore.
Nobody told me.
Please, can we have
Somebody
API?
should have told me that.
Can we have GPT tokens? And yeah, so this trade-off on what level are you analyzing is important. Maybe if you have a lot of documents, like full documents or full paragraphs, it could be very worth to input those. But again, like splitting into sentences it doesn't require a huge effort, and why not? So we run this on the classic standard BERT pipeline. I didn't make any big changes I just had to define a large language model. In this case, I use a BERT-based embedding model, a very lightweight. I tried to use OpenAI. At some point, it failed because of unknown bugs. And then also later, I was worried about the ethical considerations of just putting that in OpenAI servers. Whereas the one I use, I just download it on my computer and I run it locally. So you get rid of all of these like ethical research concerns when it comes to generative AI and research data. In the output, I got 34 topics for the study of science, 23 topics for the essays. I could not identify any topics in the interest, and 21 topics in the keywords. And I want to show mostly my process here between this and this, because I think that is like why we're here for mostly. Like I think it was very interesting for me to handle this algorithm, which I don't specialize on this, so I was learning on the go. First, the sample size and nature of the data can affect in many ways the algorithm. I saw many different examples out there on the internet, and it's a bit unexpected the way things can go on. So, for example, the reported interests were highly unstructured. We got documents that are said well, Ben provided a template on how to introduce yourself. We tried to give it a structure because it was aligned with the whole experiment we have designed.
I'm not sure if anyone can follow the idea that most people here went in the course.
Yeah, but the thing is that I struggle to explain the whole experiment without explaining the whole experiment.
You have Moodle there, you just show them the slide.
That takes too much time. Okay. The thing is that thing still failed.
There it is. So you're supposed to describe your interests in this regard, in
these 6 categories.
the 6 categories.
And then Ben gave an example on how to introduce. I am interested in using machine learning. And yeah, every word was associated with a category. So some students followed this template very accurately. They said I am Pip, I am interested in using ChatGPT. They put how they call these things?
Braces.
Braces? AI tool to study a lot in school, braces, environment. So that is not a normal way to write a text also. But at least it was structured. And I think if we would have gotten all students to follow this structure, maybe I could have extracted something around that, particularly because I could have focused on the keywords since they were associated with a brace, that allows for that. The issue is that some people didn't follow this template, or instead, sometimes they didn't even introduce themselves and just ask questions, which is fine. It's an introductory assignment, so there was a high variability on how they expressed themselves here. And the fact that they were short, that they could not be split in many sentences, made it hard to make enough samples for the topic modeling. So what I ended up having is some visualization like this. I have 2 groups. Each one of these points is a different sentence. And there was no clear-cut clusters of topics. Maybe here it looks like it, but when I hover over the documents, nothing made any sense. Again, this is very subjective interpretation and assessment on what is going on. On the other hand, we had the full prompts. I have 78 prompts, which is when students were asking GPT to produce something for them. And here we had prompts that were too structured, because the way they would interact with ChatGPT is that they would say, create me something to explore, describe me a scenario, predict a future scenario, or to exploit, they would ask for more details. And these prompts were, they had templates like the structure of the prompt was given by us, and they would change the keywords, like the main concepts that they were looking for. And here in the full prompts, I identified two groups, one for the exploration prompts and one for the exploitation prompts, which when I saw it was like, oh, this is cool. But again, it was like kind of expected now that I think about it. Like, and yeah, here the semantics are not very important, but more about like the structure it or like the overall sentence, like what it's supposed to do. So the way we came around that is using the keywords instead of the full prompts. But yeah, so those are examples of failed extractions of any topics that were relevant for us. The way I think produced more results, like more interpretable results, was tuning the HDBS, the clustering method, density-based clustering method.
So the implication of that process would be that you can't use this method to explore latent structure in already structured data, but you're just going to get back the structure that you put in. Right. So if you have your game software, there's for some reason that I wouldn't know myself, but you might know that there's some structure on the data that you get out as a result. Then it's going to be, yeah.
But I think there is something to add. Because if you have the structure and you know the structure, then you can remove the important parts of that structure, which is exactly what we did here.
Sure, but it remains a complication if you have to do the removal, and that's some data science work, or at least just data wrangling work, and you have to then have something to do it. So
yeah,
like it needs to be known. It needs to be known
It is, but this is about the prompt that the students were giving, like guided prompt. But then I guess the point in this other case is that, okay, what are the exact discussions they have? So did you already also have here the further discussions, or just the prompt that you were analyzing?
Just the prompt.
Yeah, and in your case, I mean,
it would be the discussion.
So so it matters maybe only in the sense of what's the scale at which you enter the data.
Yeah.
So if you have the discussions and then they all follow the same sort of back and forth with the same character, maybe if you enter whole conversations, it might be a bit too pre-structured. So if you enter just single utterances, single lines of whatever people were players were saying, or the character was saying back to them, but remove them from the structure of the conversation. Just try to put you in mind of this kind of issues before you get to it.
And what is also interesting to see, okay, whether, again, it comes out with the sample size. So for example, here I observe different, like two clusters, one for each prompt, which are distinguished by its structure, but then I could just take one cluster. So I just take the exploration prompts or just the exploitation prompts, and I ran the model on that. So instead of creating me two clusters that are highly dissociated, we just focus here and try to extract the little nuances between that. But to do that, we need like many more data points. Like the more close they are semantically, the more data you will need to like get these subtleties. So yeah, now I wanted to talk about the HDB scan, because this is what I was tuning mostly. Here are two parameters that are quite important. First is the minimum cluster size. This here I have a data set, it's a toy data set example, where two clusters. So we have like two very tight ones and two more like sparse, wide. I don't know the proper word, I think sparse ones, with a total of 4 clusters. So
homogeneous and heterogeneous.
Okay. And then we have the minimum cluster size defines like, how many points does a group needs to contain to be defined as a cluster. If I define, where is it? Okay, so it starts with a minimum cluster size of 5 that correctly identifies 4 clusters. And then if I go down to, for example, a minimum cluster size of 3, then I have 90 clusters, and these bigger clusters are getting like, with different clusters inside them, and also for the more compact one. And then if I raise it too much, what happens? I still have 4 clusters, but these clusters, I think what happens here is that they don't contain much of the outliers. So the more, it's a thing of data size, like the cluster size is gonna be very sensible for noise. So the more data size you have, if you can increase the cluster size, try to do it as much as possible. But at some point, like you can like neglect some smaller clusters that are very important as well. I don't know, like if we have a minimum cluster size of 100, then there might be some group of sentences of documents that are just 50 or 60, but they are still important. So you need to like figure out how much you care about these little nuanced outliers that could be clusters or not. Then the other one was
about overfitting.
Yeah. And the minimum samples are like, okay, how many in the algorithm? Oh, this one is very hard to explain. So the algorithm is taking a random point and checking how many points are around it nearby. If there are, for example, 5 points, then all of those 5 points are part of the cluster and it's gonna expand. If around that cluster, here in the minimum sample is 5, if around this point, for example, I don't have 5 neighbors in a little circle that is defined by the algorithm, then the algorithm stops there. So this quite of defines a lot of like the borders of the cluster, of how fast or not they expand to the edges. So for example, here we have a higher minimum samples, and this is not capturing this, like it's including less of the borders of this more sparse. It affects mainly the sparse clusters, not much this tightly compact one. Whereas if I have a minimum samples of 5, it captures more of the borders. And this, for example, helps a lot taking in the outliers, like to classify previously unclassified stuff. The minimum cluster size is basically how much you zoom out or you zoom in. So for example, in concrete, in my data, for the study design, I had two extremes of this parameter. And if I set a cluster size of 10, I have 2 clusters that covers every point of data. It doesn't leave anything unclassified. And these are defined by assessment, study, educational. And the other cluster is ChatGPT, academic writing. So yeah, this is about academic writing and GPT, and this is everything else. It's mostly about education, AI in education, assessment, blah, blah. Now, if I go to the other extreme, like a very small cluster size, then I have a lot of minimum, like I have a total of 138 topics and a lot of small, a lot of small clusters. And once you review the clusters, they're like, yeah, many of them are okay, but it's too granular. They're like, sometimes if you see 2 of them, like these ones that are together, they all kind of like, okay, so for example, this, the ChatGPT and academic writing, yeah, it's loosely defined as GPT and academic writing. I would say they were like different in a sense, like because there were many people that mentioned ChatGPT without including writing or academic writing. But still, like, why would you make so many different clusters for something that I interpret as like only maybe 1 or 2? So again, there's a lot of like subjective interpretation. Like, okay, where do you see the difference? Do I see it? No. So this is not useful for me. And I tried to convince myself that that was a rational decision to me, which is the hardest part. Yeah.
You mentioned before about hierarchical clustering. So DBScan, is it hierarchical?
Yeah.
Okay.
So I have.
Are you going to cover that?
Not in this one. Okay. I had the dendrite, you call it?
Yeah. Dendrogram.
Dendrogram. The issue is that the distance between all of my clusters is very small. So do you remember the example where I had like, this is a very happy person, this is a very happy dog?
Yeah.
Like in this case, I assume because the embedding model I was using is very general, all of these documents are classified towards the same direction, you know? So like the difference between them are very subtle compared to like the news group where you have documents talking about sports. You know, like sports doesn't appear here, but I think like with well, there is one of these edges is like home economics that makes its own particular cluster. But yeah, I think it's about that. Like the hierarchical one like failed for me to like make sense. But again, like I'm not so I don't know much about the hierarchical, mostly because it didn't make sense in my own results. But that is a very user personal error.
Points. This makes me think that you have to be extremely careful of remembering how your analysis is being produced, in the sense that, like you said, first of all, not to interpret the topics you see as being analyzed like purely within their own universe. They're analyzed with respect to some model which is trained on some other universe of data.
Yeah.
And then they're interpreted, or their value lies inside of that universe.
Yeah.
Their model is trained against. And then the other thing is, if you look at something like cluster size 2 clusters, you have to be very careful. That's would lead you to massively overfitting in an interpretive sense, like subjectively overfitting, if you're not careful, or if you forget that what you're seeing is just a very it's a computation or an algorithmic output. So I think that it's easy to forget when you see words, to forget that they don't contain intrinsic meaning. The meaning assigned to them here is generated by a particular algorithmic process. So you should be careful.
Yeah, I mean, I think like, of course, in every case, having a fine-tuned embedding model is going to be like the kind of optimal choice. But yeah, then we enter a different realm of training embedding models, or like doing this kind of stuff, which is not it's not an impossible task. I would say like these embedding models are not ultra hard to train as a large language model, for example. Well, besides that, I ended up with a minimum cluster size of 10, which is what the developer recommended. I just lowered the minimum samples from 10 to 5. That was the only change I made after like many iterations. And it gave a satisfying outcome in my head. There was one topic that I felt it was very out of place, which was this number 9, Kendall, 2016, 2019, which were inline citations. Like in there, of course, like they were making study designs, so they would cite other studies. Even though I removed the bibliography and the reference sections, there was no way to remove them, so they just stayed there. I just manually removed it afterwards. And then this one, the AI education, AI academic, is this big orange block. It was the largest group. It covers like 20% of the documents, more or less. And it's very broad and general. Like there are like many, I would say, subtopics there that it didn't like separate it very well. So yeah, that was a bit of an issue. In any iteration that you run this, you end up with that. And I had clusters that were like defined by one person and only one person, and some others that were shared between people. So for example, the ChatGPT students, that was like more broadly covered by different participants. But for example, the image generators, which I think is this tiny block here, is covered by one person, and so on. Then I had the keywords. The keywords is interesting because it looks differently, not only because there are fewer points, but also because the keywords of the prompts, they were like extremely similar. So for example, where is this one is ChatGPT, I think. These ones. And they look like they're like tightly one over the other. And the only differences is that some of them are like all in caps. Some of them just say GPT and not ChatGPT. Some put ChatGPT 4. Some put ChatGPT the slash 4. And yeah, that produces this. And it just clusters that. And here we have more of a difference. Like here there's individual learning, digital literacy. Like this is a block. Many of them are synonyms. Some of them are not. Some of them are learning or enhancing understanding, developing cognitive skills, something like that. And yeah. And these require a minimum cluster size because the clusters were, the sample size was smaller. So to find cluster, I just needed to reduce the size of those potential clusters, since we didn't have like thousands of data points as I had in the previous one. And then a very not so good looking graph. This is like the topics per class distribution, which is what I tried to show before, but I was a bit confused. So each class here is a different student. And these are the topics distribution in their essays. So how many sentences are assigned to any particular topic. So for example, this number 9 has a lot of these sentences in one of these colors. I cannot read. Like this coloring and graph is very non-informative. I think it's about creativity. Not wrong. And then this is the kind of information that we wanted to extract, because from this we can extract like how diverse their assignments were. So for example, someone who focused much more on one particular topic, opposed to, I don't know, someone who has more diverse or like a different set of topics, or like maybe they focus on one, but then they show others as well. Like how do we quantify the diversity, and what can that tell us of in our own study? So
this kind of visualization should only be used with ordinal data. Doesn't make sense with categorically.
Okay. I don't like this one, but I didn't have any fun.
Because it's not ordinal.
And well, so how do we measure that? We'll go fast on this because maybe this is not on point. There is a Shannon diversity index that they use in ecology that comes from information theory, actually, that just measures like species abundance on some ecosystem. So somewhere where there is a dominance of one single species will have a lower Shannon entropy number, and someone has more even distribution will have a higher number. So higher is more diverse, lower and less diverse, more concentrated in one. So with that, we quantified how topically diverse their qualitative data was. And we got two like kind of results for our own study. We found that higher topic diversity of prompt keywords for the participants. We found a higher topic diversity of prompt keywords in the prompts. Oh, this was horrible. Yeah, there is a high topic diversity in the prompt keywords for participants that use more exploration prompts. So in their interaction, it's more topically diverse when they use more exploration prompts, which is not surprising. Like it's kind of expected, but I find it nice that we could like give it a quantifiable support of that statement that exploration effectively brings more topical diversity into their interactions. And then on the other side, we found that a lower diversity on the essays it was correlated with a higher use of GPT keywords. So people who were exploiting information that they saw on their chat with GPT, later they displayed less topical diversity on their essays. They focused more on one topic. So maybe they were like already like very focused on one single topic. They created something in GPT. They found what they liked in their answer. They went through. And then we just saw that on the essays, like their specialization. I think I have a better way of saying that, but that is on what I was writing. And I want to finish with a practical advice. First, just give it a try. I uploaded an example in a Google Colab. It's in the Moodle. It's just a web page. You follow the instruction, you click play on some things, and it will do the topic modeling on this 20 news group that I've been showing some plots about. It doesn't require to install any Python or programming libraries or anything like that. It's just go there with your Google account, I think, and press play. Depending on the task you have, data pre-processing might be the main challenge. Again, like how do you extract the text and put it either on sentence or the document level, and how you clean that text, how you remove, I don't know, like references in my case, or other things that you might care about. It was important to note because some participants were using some word, something to write, that WPS, this Chinese version of Word, right? Is that WPS?
Yes.
So I assume, because it was on the metadata of their documents, when I was converting their text into Python, it would like come out horribly. So I had to process those documents in particular. And that was a bit exhausting because, well, they were 3. So it was not that exhausting because they were small. But if you are in a bigger scale and you don't have control on where the participants are writing their stuff, that might be challenging. So I don't know, for example, if you have your platform, probably you centralize the writing, or like wherever the text is being produced. But in our case, we didn't. Like every participant had their own software, their own computers, and yeah, these small outliers of 3 participants, they use a software that didn't talk very well with Python, so the text was almost lost.
And we had got a small sample, we couldn't just cut them out.
Yeah, exactly. It was so small that I could do it myself, so it was not like the bigger issue, but it's not a scalable issue. So if the topics don't make sense, just tune the clustering algorithm. Maybe I made it sound, there is an N here. Maybe I made it sound too hard, but in practice, it's about modifying a number, playing it again, and see what happens. I think the harder is to like interpret that and like how to make the right decisions on towards where to tune it to get bigger clusters, more ill-defined clusters, or like very super specific tiny ones. If you have and this is important. If you have any predefined topics or a coding framework, which is very usual in qualitative studies, you can use them in a semi-supervised way. So instead of just having BERTopic find out whatever it is in your text, you can guide it. I don't know, like if you have a category, I don't know, I want to distinguish feelings, and I have like positive feelings, negative feelings. You can give an example. You can just give the category that you want to see. So either the category or some document category. So positive feeling is like, oh, I feel so good. Oh, this day was so nice. And you pair them and you provide them as some kind of seed. And then the whole algorithm is gonna try to find documents that are similar to those. And if there is no documents, then the model will not classify them. It's not going to force the model in a certain way. Just going to make the cluster if the cluster really exists in accordance to the clustering method. It's going to look in a particular space in the embedding. In the embeddings.
Not sure if I followed, but use a semi-supervised method for what? To get you.
to define the topics. So for example, these clustering methods are defined as unsupervised learning,
Yeah.
right?
So
So
clustering step, you use
when you input the data, I don't fully know the details because this is not what I did.
in the user's sense, then, in order to get the predefined topics in as categories, you just have you can just do that as, you can enter them as an argument to the code.
Yeah, you can give the categories, and then it will get an embedding of the category.
Yeah.
So how you define that category is important, like the label. Or you can give labeled data, like the category with examples, basically. So you can put it in the data set, for example, as rows. So in a row, you have a piece of text, you create a new column with a label, a category, and you put like, this is positive, negative, positive, negative. And you put that as part of your data set, and it's gonna guide the framework towards there. I don't know the details. I just know there is the option. Like again, there are like many ways to use BERTopic. I just use the more standard of the shell, but moving to the semi-supervised is not that hard. So what the future might hold, I think this framework is very interesting. Topic modeling is not a new thing. There has been other algorithms before, but I think this one is very flexible. It's constantly evolving. I think the other one that is very used is called LDA or something like that. I don't know if you've heard that. Could be. Do you know one, maybe? Have you heard about any other topic modeling algorithm? LDA? LDA?
Yeah, it's very commonly used in bibliometric studies.
Yeah,
Where we
not
not
specific to topic modeling, it's just some kind of a latent.
And in bibliometric studies, we don't exactly follow this topic modeling procedure. We mostly only use this most representative words weighting precise, which is this TD-IDF.
Yes.
But we also use mutual information actually. So not exactly the same, but like we have this small subset of methods used to identify.
Yeah. So like what I see is that, okay, it's a very used method, but what I understand from it, like I read a few, but not much, is that it's already defined. It's like a static method. It's not like, for example, this where like the output of this model depends a lot of like the embeddings and the technology behind the embeddings and the evolution behind the large language models. So I think there is a lot of promise in that kind of thing. Also, I don't know if I mentioned it. Yeah, okay. So one point is decomposing large language models, which there are like some very interesting papers and research going on about this. This is an example from something that Genia shared like some months ago, where Anthropic were like extracting patterns from neural activations. So for example, what I just presented is just using the output, like the final layer of this neural network. But this research is analyzing the whole like pattern of multi-layer activations, and is extracting features like interpretable features, and you can tune that. You can try to understand why some things are closer to each other, and it's very interesting. I will probably upload some sources that I will not have any time to show you anymore to the Moodle, where you can actually enter this feature space and hover over, like see around like what are these clusters and how they're defined. And then also I think very, very profitable ways to train models to other types of sequential data, which I think is something that we can try not only for like, for example, the streaming thing, but any kind of sequence can be modeled by this, it can be embedded somehow in a vector and inserted into the same pipeline. Like again, it's just changing the first block of the embeddings. You change the data, but then the dimensionality reduction, the clustering, and the frequent feature like presence of each cluster. I think it's a very it's a workflow that you see a lot of different machine learning like tasks. It's not unique here, but it's well packed, I would say. And the fact that it's open source and you can just get in the hood and edit everything, it makes it much better. And that's it. Thank you very much for listening. Okay, so you mentioned, I feel qualitative interpretability of the clusters identified should have an important role in deciding the minimum cluster size. Yeah.
I agree that maybe it can be from the point of starting doing the clustering, then you have kind of assigning the meaning to cluster. And so maybe it should be kind of iterative thing. So you decide clustering and kind of in the iteration, you check that are they meaningful enough? So you decide some threshold when they're meaningful.
Yeah.
So that sounds like a job for the kind of methods that have been designed for like expertise elicitation, kind of thing we looked at in the Avalanche project, Delphi and analytical hierarchical process. But it sounds like really laborious. That's those methods. I mean, how to make judgment when is it meaningful enough? This has always been a challenge for me coming from a data mining background. Like I hate that feeling of subjectivity of making these judgments, which really disturbs me somehow on an aesthetic level.
Yes, that's true.
Just for my, I don't know, maybe my brain's a bit weird, but yeah. So you could do that process you mentioned, but I'm not sure how to make it like scalable.
Yes, maybe ChatGPT.
So yeah, some real machine learning.
Yeah. Maybe you ask like 100 times ChatGPT, and when you reach the maximum percentage of the positive. I don't know.
Yeah, some asymptotic.
Okay, so for example, this I think is a very nice visualization, this issue on whether we can capture structure or not. So for example, this is a UMAP and you can tune the parameters. So you can say, okay, like if I set this to the minimum, I don't want to explain what is this doing, but then I don't have anything. And as I increase, I slowly get something, but it's still like, it doesn't even look like the ancient cave paintings, you know? It's like, it's that, but maybe on like psychotropics or something like that. But you can still like say, okay, like this is a mammoth, by the way, the skeleton of a mammoth. There are 50,000 points of its geometrical like shape. And yeah, you have like the horse, how do you call this? Whatever, tusks. The tail, tusk. And you can say like, okay, maybe it makes some kind of sense, but you can say that just because you know that it's a mammoth, like you know like the 3D structure of this when you are trying to interpret this 2D map. But if I just show you like something like this, like you don't have anything. Here is a nice comparison between the TSNE and the mammoth one.
Actually, that looks more similar.
Oh, do you like it more, or is it like an aesthetic?
To be honest, but probably they were doing TSA.
Yeah, but this took, for example, this took 2 hours.
Okay.
And this only takes 3 minutes. So this is about the performance of the models. But yeah, like I think you cannot like disregard, like these are not all of them, but many of my iterations on one type of data, only one. And then it's like, yeah, when do you stop? Because the problem with DBScan and the UMAP is that they are like they're non-deterministic methods. So there is never a right answer. Like even if you...
One thing that should be done here, which maybe I've not done it before in my work, but it's definitely like when you're using data mining pipelines and you have to adjust the parameters and then judge the outcome, that's a multi-step process. What you should be doing is having parameter sweeping, and then judgment is a single step process for you. So you have all the outputs and you judge them on some subjective criterion, and then you pick one, and then you go back and look at which parameters does it have. Anyway, we're running out of time, so next one is in a month on Monday the 28th. Who will be here?
Can I pick?
Who will be in Uusimaa State? That's a small enough region. Well, you'll be here.
What?
You'll be here.
When? Yes.
Monday the 28th.
I guess so, yeah.
Okay. You will be here, Lisa? You here? Sonia? No. You'll be here.
Latent class analysis, you can formally statistically compare the goodness of
Right. So Natalia will present the month.
Could you describe me how
What rats and
is that
people
goodness extracted?
project. You're going to
Like, do you start from the assumption that you know the classes that you have, for example?
Again, I've used latent class analysis only once, and I'm definitely not an expert, and I missed the beginning part of this talk, so this may not be relevant at all. I was just wondering, because I was looking at the, I mean, you have a lot of different clustering options, like you can tune the algorithm to produce you specific types of clusters based on the minimum number of observations, but I didn't see any kind of formal comparison that might help you guide. For example, if you just decide to have as many observations, that gives you like 4 clusters. I mean, you can always just decrease the number of observations and arrive at 5 clusters, but can you formally compare the kind of the goodness of that solution, like the goodness of the 4 cluster solution against the goodness of fit of sort of the 5 cluster solution? I don't think you can, because this is not like a formal modeling technique, and latent class analysis is a formal modeling technique, similar to clustering methods. But it enables you to kind of statistically compare the goodness of it using, for example, Bayesian information criteria numbers and so forth of different types of class solutions. Again, I don't want to go into any more details because I couldn't. I've used it once, and it's pretty involved. So I was just curious about.
Can I ask you to just repeat that, because we didn't hear anything?
The first half, because
that's nice. Sure. Anyway, so very briefly, I missed the first half of the talk, so this may not be relevant. I was just interested because you had many options for different cluster sizes based on like the minimum number of observations, correct? And I was wondering if there's any formal way to evaluate whether a 5 cluster solution is better than a 3 cluster solution. But this is not, as far as I understand, clustering techniques are not such that they yield you like a modeling framework where you can evaluate the goodness of fit in the same way that you could do in, for example, a latent class analysis framework, which is a formal modeling technique for modeling latent
I don't
classes.
know LCA very well, but in clustering there are various criteria that you can pay attention to depending on what you're trying to achieve, such as variance and things like that within the clusters.
So the eigenvalues?
Yeah.
Like there are like, because they assume there are some kind of linear relationships between the variables. So based on that assumption, they can, maximize the variance or look for like the this kind of quantifiable values, find the optimal, and that's why they are more deterministic. But then in the UMAP, like both in the dimensionality reduction and in the clustering, we have a non-deterministic method. Like they follow non-linear process to like be able to capture these more complex non-linear topologies or relations. So I actually think there is a discussion on whether the transformers, like the large language models and architectures, are linear or not. And if they are linear, like, yeah, like, does that mean like we can make some assumptions on their outcomes, that there are some latent features that can be like, I don't know, like I think that is a very interesting discussion in this particular context. But I find it really hard to even frame it in my head in a
We can come back to this later because I need to better formulate my question, I feel. But anyway, thanks for the talk, and again, sorry for missing the first half, but it was still good. Thanks a lot.
Thank you.
Thank you for being here, Jussi.
Thanks, Leo, for paying attention when you've apparently been ill. I hope you got something there and you can help Ulla later. All right. Ciao.
Ciao, ciao.
Ciao, ciao.